we can do it right now. Okay, there are many parts, so that I avoid to forget. So there are many parts that you can read just because of curiosity. So the introduction basically was the first lesson. Then we started from the Coriolis force. Okay. So of course all the part relating to numerical approach, numerical convergence. I mean, if you are interested, you can read it. Otherwise, it's not part of the course. Okay. So then we talk about the equation of fluid motion up to, let's say, the Bussiness approximation 3.7, and then this was you can read it. I mean, it's not requested, but it's something that you can know by knowledge. Here it's important the scales of motion, the recapitulation of the equations, and the dimensionless number. This chapter here we didn't treat, but as well, if you like, you can read it, because it's very, I mean, it's very light lecture. It's not too much deep as other books of geophysical fluid dynamics. If you look for Pedlowski, for example, Joseph Pedlowski was a mathematician, and it's very, very strong, very hard. I mean, mathematically speaking, if you are a mathematician, maybe you can enjoy. If you are not, maybe it can be boring, especially if you are not interested to work with that. The same with chapter 6, and then we started for chapter 7. Okay, so we will do today this one. But I think I will send you an email, so with the precise chapter and sections. Okay, so yesterday we introduced the geostrophic flows. So geostrophic flows are geostrophic flows are characterized by the fact that we have the temporal Rossby number much smaller than 1, the Rossby number much smaller than 1, the Ekman number much smaller than 1, and the homogeneous condition. Okay, so no variation of density. Okay, then we understand that the governing equation were strongly simplified, and what we found was that the variation of the horizontal velocity, okay, I can write it also here, so of the x component of velocity and y component of velocity is 0, okay? This is also called Taylor-Rudman theorem, okay? This is the name that you can find in the syllabus, which actually tells you that the flows that satisfies this condition don't have any shear, okay? So flows are like this. So there is no change in the vertical of the horizontal velocity. The other thing that we found was that the velocity is perpendicular to the pressure gradient. And then we understand that according to the fact that F is positive or negative, so which means that we are in the northern hemisphere or in the southern hemisphere, usually the flow circulates in a clockwise direction with respect to high pressure center and anti-clockwise direction with respect to low pressure center. The other thing that we found was the so-called F-plane approximation, which tells us that the variation, the meridional variation, okay, on the northward axis of F is 0, or very, very small. So this can help us to find that the horizontal divergence is 0, okay? And so we said that geostrophic flows on F-plane are non-divergent. Okay, so what we did so far was for a flat bottom, okay? We never talk about what is the bottom, how is the bottom, but we hypothesize that the bottom is flat. So what happens if the bottom has a sort of inclination, okay? So let's think about that we have a layer of the flow. There is some sort of discontinuity here, and we can impose here. So this discontinuity may have, for example, scale which has a value of eta, which is much smaller of capital H, which is so this is Z. So this is capital H, the total height of our system, and this we can call it H, but with a small case, which is a function of x and y, which actually we can think about as a bathymetry, okay? So we can think that this is the ocean, okay? This is the surface of the ocean, and this is the bathymetry, and this is the bottom of the ocean, okay? So a point here will have a vertical coordinate z, which will be equal to capital H minus h, which is a function of x and y. So according to the position, of course, I can have a different depth, okay? Like the bathymetry in the ocean. Okay, so if I am here, if I am a parcel here, would it be possible to climb up or to go down? This is the question that we want to answer today. So it would be possible that being on this sloping bottom, the parcel will go up or will go down. What do you think? I mean, this is pure intuition.
Go up. I think from rest.
Staying for rest. Okay, one for rest. Other ideas?
No, I mean, if it starts from rest, then it's going down.
No, we can, well, this is a good point, yeah. We can say that it has a radial velocity. Because, of course, if you remember what we did here, so when we impose it like this, it means that all the time derivative is equal to 0. So we are looking always to steady condition. Mm-hmm. So think about that this fluid is moving geostrophically, so it's still a geostrophic flow. So for some reason, this bottom starts to be inclined. What do you think? Goes up, goes down? Other solution? Don't worry. Any ideas? You can bet.
I think maybe it depends on the direction of the flow.
Depends on the direction of the flow, yes, could be. I'm just taking some idea. So, do you think, okay, let's think, let's say that we call it in, it's reductio absurdo, something like that. Is in Latin, okay? So in Italian we say per assurdo. So it means that we are going to think, okay, let's think that it wants to climb up. Okay? So if it climbs up, it means that it will have a vertical component and, if this is x, a x component of velocity. Okay? So let's try to express w. So w, which is the vertical velocity, is basically the total derivative of z, of the vertical position, with respect to time. So this is the total derivative. We can decompose it in the local derivative in time, plus the advection. So we will have u, the z, the x, plus v, the z, the y, plus w, the z, the z. Okay? But, so z is a function, since capital H is a constant, z is a function only of x and y. So we can say that this term we doesn't need, and this term we doesn't need. Okay? But what we know, we said before that at this discontinuity, w capital H is equal to 0. Okay? So this is something that we imposed as a boundary condition. Don't forget that when we are working with the geostrophic flow, somehow we are losing a boundary condition, which is related to the friction, because we are not, we lost the second derivative, okay, which was related to the horizontal and vertical friction. So we have to somehow allow the slipping on the bottom. But here we can say that WH is equal to 0. But we know also that for geostrophic flow in F-plane, we have that the horizontal divergence is equal to 0, which means then the vertical velocity must be constant. So it means that if here it is 0, it must be 0 everywhere. So vertical velocity is 0. So it is not possible that the flow go up or down. So what it means? It means that if we solve for this and we substitute this expression here, what we will have is that 0 is equal to minus u dxh minus v dyh. Okay, so I'm just substituting the value of the position, the vertical position, in the two derivative. So this form here, which can be also written like u, which is perpendicular to the gradient of h. The gradient of h, the horizontal gradient of h, is nothing more than the map, if you like, of the bathymetry, because this says you how h, for example, change on this direction or in the other direction. So this means that the velocity must be always normal to the gradient. So it means that the velocity can be only on this or on this. Okay? So the only possibility is that for a geostrophic flow on the F-plane, which are going to satisfy our hypothesis, if we have inclined bottom, this can only move over the isobath. Okay? So isobath are the lines of equal bathymetry, which are equal to isobars. Okay? Which are the line of equal pressure. Okay? So this is a quite strong condition, and if, for example, we think about something a little more real, like, for example, a system which has a bump, or, for example, a hole. So if I have a flow which is going up, which are coming out from the blackboard, So the flow can be only turned around the obstacle. It will not possible that the flow will jump from one side to the other side. Okay? So this is extremely important and gives this property of vertical rigidity to the geostrophic flows. Okay? So it means that this kind of flows will maintain their position and their characteristics, even if they are impacted to an obstacle. And if you think about that, this characteristic you have along the entire depth of the fluid, so it means that, and the velocity here at a certain z1 will be equal to the velocity here, and so on. Okay, the horizontal or the the zonal or the meridional velocity, so along the x or along the epsilon. So it means that in this occasion, in this configuration, you will have some sort of columns. Okay, and these are called Taylor columns. Okay, so Taylor columns are sort of flow patterns typical of the geostrophic flows over, let's say, disturbed bottom, where we are using the F-plane approximation. Okay, so it's quite rigid. The geostrophic flow can help us to explain flows like this, or like this. Oh, sorry. But of course, it's quite limited. Okay, so it's very nice as a model because it's quite clean. No, we have very nice equations that we can solve, and we are very happy for that. But it's a little bit too much limited. So since it's too much limited, what we want to do is to try to relax a little bit our hypothesis. Okay? So it means, in particular, that we will maintain the homogeneous fluid. We will maintain the fact that Ekman number is much smaller than 1, which means that we are not considering any kind of frictional effect. So in some sense, we are quite far from the boundary layer. But we give the opportunity to the flow to be a little bit less slow. Okay? So before, we had the time scale much longer than the rotational scale, okay, so much longer than 24 hours. Now we are approaching to the rotational time scale. So we are going to have maybe a few days or something, okay, or 1 day. Okay, with this too relaxed hypothesis, if you remember from the scale analysis of the equation, we can keep the variation, the local variation in time of velocity, because this is no longer so negligible with respect to the Coriolis term. We can also keep the advection. Of course, we have all the other terms. Then what we have is that since we are still looking for homogeneous fluid, the hydrostatic condition is simply the constant of pressure along the depth. And finally, we have our continuity equation. Okay, so what we did, we practically, in some sense, we moved from considering flows with a very long, very large, let's say, time scale with respect to the rotation of Earth, to some flow which are a little bit more faster, let's say. Okay, but geostrophy, which is basically based on the Taylor-Putman theorem, still work. I mean, I'm just moved from a geostrophic flow to something a little bit different, which is called barotropic. Which still keep these characteristics. Okay, so if this characteristic is true at t equal to 0, at the beginning of our time, there is no reason that this change in time. So we can easily neglect this term here, where we have the variation of u and v with respect to z. Okay, so we still keep this this condition. The Taylor-Putman theorem is still valid, even if, or let's say, this condition is still valid. Taylor-Putman theorem is depends on the fact that we have the two Rossby number much smaller than 1, because that was the demonstration of the Taylor-Putman. But still, we are considering, so we want to still consider a kind of flow which are no shear, okay, without shear, without vertical shear. So with this new, okay. It's okay. I thought there was something broken. So with this new hypothesis, we are going to consider new kind of flows which are called barotropic. Okay. So this is the third case. First case, inertial oscillation, very simple. Second case, geostrophic flow. Third case, barotropic flows. Okay. Slightly, a little bit more difficult. Okay. So barotropic flows, apart from this, don't have anything in common with geostrophic flow, because we cannot say no longer this. So we cannot, of course, solve easily u and v as before, because before we only had this one. Okay, so it was very easy to solve for u and v. Now we have let's say a real partial differential equation at first order. So all this part here is no longer valid. So in this sense, we can say that barotropic flow can allow a divergence in the horizontal. So let's try to see what happened, for example, if we consider a condition which is similar to the previous one, where we have, again, a 2D view. So we are considering a slice of, again, let's say, water or air. This is our bottom. So the bottom is defined by a function v, which depends on x and y. And this distance here is a function h of x, y, and also t. Okay? So this is practically, I am looking to a single fluid column. Okay? A fluid column that I suppose will be moved, transported by the flow. Okay? And will interact with the bathymetry. Okay, so let's try to express this with the derivative. And to integrate over our fluid depth. So from B to B plus H in dz, and still is equal to 0, of course. Okay. So I'm going to integrate the continuity equation over the fluid depth. What happens? So it's quite easy. I mean, these two parts, don't forget, we are still working with the no shear fluid flow. So we can move this part because they do not depend on the z, on the vertical. So if we move this, what we will have will be simply du dx plus dv dy b plus h dz plus, when we want to derive this one, to integrate this one, what we will have will be simply w calculated in b plus h minus w calculated on b. Okay? So now we are not saying anything about the value of the vertical velocity at the two boundaries. Okay? So this is something that it's another strong difference with the case that we analyzed before. Okay, so this is still equal to 0. So this is quite easy because this is simply h. Okay, because it's b plus h minus b. Okay. So let's see what we obtain with the first term. So w calculated in b plus h. So we will have, so w is again dz over dt calculated in b plus h, which will be partial derivative of z, which is b plus h. But the partial derivative of t applies only on h, because b doesn't depend on t. So I have only dh over dt. Okay? So I'm simply, don't be lost, so I add one passage. So it's like, I'm doing this operation, okay? And I'm expanding this operation, as usual, in the local derivative and in the advection term, okay? So this will be equal to okay, plus u plus v and then z is 0 because b and h do not depend on z. Okay. So this is also 0. So what we obtain is this term here and these two terms here. So I will have u dv dx plus u dh dx plus v db dy and v db dx. Okay? So this is the value of the vertical velocity at the surface, b plus h.
I'm sorry, can you slow down a bit? I really cannot read everything.
Okay. If we slow down too much, we will never end.
And like two equations, like.
Okay. So vertical velocity calculated in b plus h. b and h are just function of x, y, and h is function of t. I just substituting the value of b plus h in z. Okay? So I'm doing dB dt plus dH dt, because I'm just substituting this in the derivative, and then I'm adding the advection term, okay? B is independent of t. B and h are independent of z, so I remain only with the local derivative of t in t with the of h, and the two horizontal advection term applied to b and h. Okay, it's not important. I mean, we are going to arrive to the result. Then you have time to review all the mathematical passage.
Excuse me, Professor. I'm wondering, what would happen if we take into consideration erosion where B changes with T?
Okay. This is another. It's a completely different point. Yeah, it's another case. It is a little bit more difficult because, of course, we are not taking into account this. Erosion is a very small scale phenomena. As you remember, one of the hypotheses of GFD is to take into account with large scale phenomena. So this will mean to apply GFD, or let's say the equation of GFD, to very small areas, and so you will have to complexify a lot all the equations. So all this kind of, let's say, framework, mathematical framework, do not apply. So we are just saying that this is a fixed, flat, smooth bottom without any kind of roughness. Otherwise, that is fluid dynamics, not just geophysical fluid dynamics. But yes, it's of course it would be a problem. Okay, so let's do the same for the other, which is vertical velocity calculated in B. Of course, if we do the same operation, what we will have will be simply the two horizontal advection term, because we will not have any dependence on t, and again we will not have any dependence on z. Okay? So when we do the difference between the two factors, these two, the b, the x, the h, the y, the b, no, sorry.
No, it's correct. The final,
This is x, and this is y. Okay, so the b the x and the b the y. No. Sorry. So this is u and v the b the x plus v the h the y. The y. Okay. So at the end, what we found is this term here, so the horizontal divergence multiplied by h plus the local derivative of h and the two advection term. Okay? So, if we look at this, we have a total local derivative, the advection, so all this become total derivative of h, and we can express this like 1 over h dh dt equal to minus horizontal divergence of the horizontal flow velocity. Okay, so this is actually the new expression for our continuity equation. Okay, so continuity equation has been integrated and has given rise to a new equation which actually takes into account the fact that we are looking to the variation in time of the fluid depth, the fluid column, which is related to only the horizontal divergence. So if I have, the idea is that if I have convergence of fluid, okay? So convergence means that this term here is negative, because by definition convergence is negative, okay? So I have convergence of fluid on the horizontal plane, which means that if I converge somewhere to conserve mass, I have to go up, okay? So if I go up or go down, it depends. In any case, the fluid column will increase its depth. So this will be positive, okay? So in time, I will have an increase of the h with respect to the incoming flow. On the other side, if I have divergence, this is positive, so with the minus I have a negative variation of h, so I will have a decreasing of the fluid depth. So we can also substitute this new equation, and we can simply write it like so dH plus HU plus dy HU HV equal to 0. Okay, so I just put together these four terms here, okay, this and these two, in this one, okay, in these two terms here. Okay. If you obviously if you derivate the singular term, you again find this expression. Okay, but we can do something more. So you remember that we defined the pressure as P0 plus P prime. Okay? So again, I'm just using the P prime. But the hydrostatic pressure was defined as a reference capital P0 pressure minus rho 0 Gz plus P prime. Okay, so this was our form for the hydrostatic pressure. So from this, I can solve for P prime. Okay, so P prime will be if I look here, P prime will be the total pressure, P, minus the reference pressure, capital P0, plus rho 0 Gz. Okay? Don't forget that this and this are P prime. Okay? Because you remember that we neglected the prime. But we know that P prime don't change in Z. What happened? It means that if we are at Z equal B plus H, which means at the surface, okay, where my total pressure is exactly equal to P0, because this was the integration constant, okay? So I am saying that the total pressure P at the surface of my fluid, B plus H, so at that vertical position equal to B plus H, is equal to P0. So I can solve P prime, since it is constant along the Z. A value that I have here will be the same along the Z, because my third momentum equation says exactly that. So if I solve this, P prime, right here, P prime solved in B plus H, it will be, so P in Z plus in B plus H is equal to P0. Then I have again P0, and then I will have plus rho 0, G, B plus H. Okay? So I can substitute my P prime, which is exactly this one, with this expression here. So the P dx will be, so rho 0 is neglected, is removed. So we will have minus G dH dx, or sorry, d plus H, and minus G dy B plus H. Okay? That's really, really, really important, because what we did actually has been to reduce our system to a system which only have 3 unknowns and 3 equations. So the 3 unknowns are U, V, and H. Because we have one equation for U, one equation for V, one equation for T. The pressure has been, in some sense, exchanged with the quantity H, with the fluid depth. And in case of flat bottom, which is a typical case, what we can have is that this term here, of course, can be removed, and what we have is simply this one. Okay? And this is called shallow water model. Okay? So shallow water model is a very nice example of a system which is let's say, an extraction or a derivation of the barotropic flow, and is frequently used also in application, because you can use shallow water model, for example, if you want to simulate lagoons where the depth is very short, but you have like you cannot, for example, you can neglect the friction, you can consider homogeneous fluid, and so on. So it's some sort of equation system that gives you the first mode of circulation, of flow circulation. Okay? Of course, when you have temperature, when you have stratification, when you have friction, you just have to add. So if you will find a solution which will be U equal to U of shallow water and V equal to V of shallow water, then you can also add other terms here, B prime, B double prime, and so on, okay, which add to the solution that you obtain from the shallow water model. Okay, but this is a sort of let's say basic flow. Okay. And it's very easy also to integrate numerically. That's why it's something, and you will find something in, if you are interested, if you will find something in on the book. Sorry, yes.
I was thinking that maybe P equal P0 at Z equals
B equal to P0 when we are here, at Z equal to B plus H. It's okay? Okay. This is something that we can, we can solve it for any depth, because you remember that the variation of P is completely independent of that. And this model is also very much used to study a real system. So here you have, for example, a map of the Mediterranean Sea with the sea level anomaly. So the sea level anomaly can be measured from the satellite. So this gives you a value which goes between -15 and 5 centimeters above the reference geoid level. Okay. So what we can see is that over all the southern part of the Mediterranean is red, so we'll have a positive value, while most of the northern part of the Mediterranean is blue, so it has a negative value. So if we use the shallow water model, but also if we consider, again, to reduce the two expressions to a simple geostrophic flow, which is even more simpler, of course. But what we can say is that looking, for example, in this point, so this is the coast in front of Egypt, so we are moving from value high of the altimetry. It's not bathymetry.
Okay.
Be careful. This is altimetry. So it is the level of the surface of the water. So it means this one. Okay. So I'm looking. Because satellite sends signal and receive the signal. Of course, if the distance is smaller, you can have a signal which is different from from the fact that so it's. If I'm here and if I sense this with respect to this, well, being on the normal of the surface, I can receive a shorter path. And so I can have a map like this. So if I'm here, this is the altimetry. So it's like this is the, let's say, the red part, and this is the blue part, okay? Because this is, if we consider this as the reference of geoid level, so this is higher than the reference, this is lower than the reference. So from here to here, it means that this is the y direction, dh over dy is positive. Is negative, because I'm going from high h to low h. Okay, so the gradient is negative. So if this is negative, there is a minus here, it means that u is positive. Okay, so this means that u is going in this direction. Okay, so if you apply this reasoning to all the points here, what you can find is the geostrophic flow in the Mediterranean Sea, okay? Which is, of course, not the surface current of the Mediterranean Sea, because surface current, as I said, is a sum of different aspects. You have also thermaline components, you have wind, of course, that we are just not considering. So, but if we look at the, let's say, bulk barotropic flow, which stays within the entire circulation in that point, we will see that the principal component of the circulation will be in that direction. Indeed, if you look at any kind of paper which represent you the circulation of the Mediterranean, the circulation of the Mediterranean starts from here, so we have lighter water coming from the Atlantic and then goes in this direction here, and then more or less come in the other direction, okay? But when it overcomes this area here where you have a little bit of meandering, but it continues to follow the coastline, which is at the end the topography. So basically it's the topography that constrains the flow, and so leave the topography level, the higher topography level, on its right. Okay, so moving in this direction.
So, Professor, are the blue areas characterized by low bathymetry? Or
No,
by
it depends.
high density water?
No, it depends. In some area can be, like for example here. This is an area where you have effectively a very deep pit. So we reach like about 1,000 meter depth with respect to, let's say, 50 meter that we have in the Northern Adriatic Sea. But not always. I mean, in first approximation we can say yes, because of course if you take a system and you put some water, of course you will have, and of course you can also consider that you should represent the water depth and take into account also the fact that you have cold water and warm water. Okay, so
I was thinking of salinity.
yeah, exactly.
For example,
Of course,
of
course.
From the Gulf of Leon is a place where there is a formation of high salinity water.
In the Gulf of Leon, we have deep convection, so which is basically due to the fact that we have strong wind stress coming from here, very cold and dry wind stress, which actually transfer momentum and energy to the surface water, which become the surface layer become let's say denser, and so it start to go down, and so we have this. And something similar also happened in this area here of the Rhodos jar, because we have very cold and dry wind from this area. So it's a sort of, let's say, first approximation. Okay, so there are of course many other components that are included in that, but of course the fact of the salinity is can be taken into account. Okay, so make a step more. And let's try to see what happens if we take the so if we take the two equations, the two x and y momentum equation, and we kind of apply, so if this is equation 1 and this is equation 2, so let's do the x. So let's do this operation. So we take the partial derivative of x of the y momentum equation, and we subtract the y derivative of the x momentum equation. Okay? So this means to take each term and derive and make the partial derivative in y for the x momentum and in x for the y momentum. So what happened is that the first, for example, will become like so minus, so I do it like this, dy dtu plus dyu dxu plus u dx dyu plus etc. Okay, so it's a little bit boring, a little bit long, so it's not let's say not constructive to lose too much time to that. You can do it by yourself. The most important thing is that when you reach this term here, this will be derived by the y, this will be derived by the x. Since we are going to make the subtraction, this term here will disappear. Okay? So what we will obtain will be a single equation which will depend on u, on v, and on h. Sorry, on f. Okay? So this typical term that you will have will be something like so if we take, for example, the first two just to have an idea, so this will be the y tu minus plus the x tv. Okay? This means that I have made the x derivative over the y component and subtracted the y derivative over the x component. Okay? So this can be also written like the time derivative of the y u plus the xv. Okay? So this expression here, can you recognize? You should recognize it from the first part of the course. I write it a little bit larger here. So it's the xv minus the yu. So this will be the first term of the new equation. Can you recognize this expression here? From the first vorticity. Yes, this is the vorticity, in particular, only the z component. So we will call this with the letter zeta, the xv minus the yu. So this is called the relative vorticity. While f, which is our Coriolis parameter, is the ambient vorticity. So all these expressions here will have a form that basically reduce to considering a relative vorticity zeta plus f. Why? So I know that the Tf is equal to 0. Okay, so the local derivative in time of the Coriolis parameter is 0 because Coriolis parameter only depends on the latitude, so at least on y, not on t. So since it is 0, I can put f here. Okay, so all these equations here that will have part of some terms with zeta, some terms of f. What Cushman says is, okay, let's gather all the terms which have zeta and f, and if we don't have f, just put it. Okay, so if we have the x of eta, I just put f, since I know that the x derivative of f is equal to 0. Okay? Same thing I will do with t, and of course with y, where I will have, because of course making the y derivative of this, I will have y derivative of f. Okay? So I'm no longer on the f plane now. Okay? So that's why I'm interested to see what happened to the divergence. So at the end, this is also left to your homework. What we will have is that we will consider the sum of the relative and the ambient vorticity, and we will have so all the operation that I did over the two equations practically reduced to this one. Okay? So we have the variation of total derivative with respect to the divergence, the horizontal divergence. So if we recover the other equation, the equation of continuity, that was written like dh over dt So now we have this equation and this equation. Okay, so this is telling us that when we change the horizontal flow, we will have an effect on the depth of the water column, of the fluid column. This is saying that if we change the divergence of the flow, we will have an effect on the vorticity, on the total vorticity of the flow. So we can also consider our column here having a cross section, okay, which we call it ds. Okay, so we take the element of our flow as a column of aspect cross section ds and height h. Okay, so the equation which governs this one, of course, is similar to this, because if I converge the flow, so I decrease, the divergence is negative, I will have a decrease of the cross-section, okay? So flow is converging, the cross-section is decreasing. Flow is diverging, the cross-section is increasing, okay? So I have three equations which relate divergence to vorticity, cross-section, and height. If I consider this and then multiply all of this by h and all of this by ds, and then I sum, because of course both of them are singularly equal to 0, so I can do it. So what I will have is that 1 over ds multiplied by h and ds plus ds over h dh is equal to 0. So this means that what we obtain is, since these two terms are equal, because what I can do is, okay, let's do it a little bit more. So I have, let's use the symbol, the dot, to represent the variation in time. So ds with the dot, which means this, okay? Which is equal to ds multiplied by the horizontal divergence. And here we have h with the dot, which is equal to minus h multiplied by the horizontal divergence. Okay? So now I'm multiplying this by h, so I will have h here and h here, and this is by ds. So ds here and ds here. Okay? And then I sum. Of course, this is positive, this is negative, so I can neglect this. And I will obtain h ds derivative plus h derivative multiplied by ds, which is equal to 0. Which means that this derivative dt h ds is equal to 0. So this means that the volume is conserved. So all of this can tell us that the volume of our fluid column is conserved, which is something that we are very happy for that. So if we do something similar, so multiplying by the quantity which is not present with this and this, so we will multiply this by the ds and this by the total vorticity, okay? So what we will obtain in this case will be something similar. The only difference is that we will have that the conserved quantity is the product between the total vorticity and the cross section. Okay? So this expression here means that the vorticity flux is conserved in time. So this expression here is nothing more than the circulation, if you remember from the first part of the course. Okay? So when I do the circulation, I apply the integral of vorticity over ds, which is equal to the flux of vorticity. Okay, flux of vorticity is exactly the circulation. So what it means? It means that when we have a fluid column like this, where it has a specific height and a specific ds with a specific f plus sigma over 2, for example, vorticity. So if it is affected by horizontal divergence, we will have an increase of surface of the cross-section, a decrease of h to conserve the mass, and also a decreasing, you see that the arrow here is smaller, a decreasing of the total vorticity. So when we increase the cross-section, we have to decrease the vorticity. When we decrease the cross-section, we have to increase the vorticity. So horizontal divergence acts in this direction, compressing the fluid column and decreasing the vorticity. Horizontal convergence acts in the other direction, expanding, squeezing the fluid column and increasing the vorticity. So this is nothing more than a conservation principle, which is exactly like the conservation of angular momentum. Exactly the same. So we are looking at the conservation of angular momentum in GFD flow, exactly like the same. So what will happen to our column here when it will travel here? So it will be contracted because it cannot overpass this barrier. It is a barrier. So it will start to be larger, okay? So to conserve the volume, the vorticity that it will have here will be decreased, and then it will still recover its dimension if we suppose that h is the same. So again increasing the vorticity. Okay? So if we consider, and if we keep, for example, f constant, so you are looking on the same zonal direction. Okay? So we are just considering this in x without any change in f, in y, and therefore in f. So what we have is just related to changes in the relative vorticity. If we keep fixed the relative vorticity and you leave the f changing, what happens is that if you change ds, it means that your fluid column will go towards north or towards south. Okay? So this principle, which is called the Kelvins Theorem, right here, Kelvin, like the one of the same person, Lord Kelvin, for the temperature. So the Kelvins Theorem is at the base of the model which explains you the general circulation of the Atlantic Ocean, which with the basis fact that you have a movement of the water towards north and then recalling of the water towards south. Okay, so still looking at these three equations, if we take the first one and the second one, okay, so since both of them are singularly conserved in time, also their ratio will be conserved in time. So we cannot, we can say that if we define a new quantity, which I call Q, which is the ratio between the total derivative, the total vorticity, and H, this is called potential vorticity. Okay? So we have relative vorticity, zeta, ambient vorticity, F, and then potential vorticity, which is the total vorticity, zeta plus F, divided by H. So potential vorticity is a quantity of the fluid which is conserved. So we can say that potential vorticity is conserved because you just take this term, this equation, you make this ratio, and you will find that the ratio is conserved. So conservation of potential vorticity is another very important aspect of geophysical fluid dynamics that actually can be used to explain, let's say, specific circulation flow in a specific area. Of course, as I said before, it's just the first mode of circulation, okay? Not just the whole circulation, because we are still working on homogeneous fluid. We are working with far from boundaries, so we are not considering the friction and so on, okay? So we can also say that if we have a Rossby number which is much smaller than 1, it means that U over L will be much smaller than omega. So U over L actually it's the scale of zeta, because zeta is the x v minus the y u. Okay, so scales like U over L. While F obviously scale like omega. So when we have Rossby number much smaller than 1, so in some sense we return back to the geostrophic flow, we can say that Q can be simply written like F over H. Okay? So we can neglect the relative vorticity and just consider the the potential vorticity as the ratio between Coriolis parameter and H. So for example, if we keep fixed F, we will keep fixed also H, which is exactly what we said before with the Taylor column. Okay? So this is the expression of the potential vorticity when we are in the geostrophic case. Okay? So the relative vorticity is much smaller with respect to the can be neglected, and so Q actually takes the form of this. If F is fixed, since the Q over dt must be 0, we have to conserve H. This is exactly what you have if you take a tank. You know that Riccardo Farnetti has a tank, a circulating tank, rotating tank. Don't you know? Some of you yes, some of you know. During the Mini Maker next year, I think you will be here. Mini Maker is a very nice event that ICTP organized, I think, in September, where all the people do something. I mean, they produce their invention, can be food or also electronic or laser or whatever. And Riccardo Fornetti always brings some a rotating table, okay? And the rotating table is very nice to look things like this, okay? So you can actually make some GFD experiment to look to the Taylor columns. So of course, in that laboratory experiment, the tank is fixed, so F is fixed. So you will see that H is fixed. So you cannot change H. H will be the same. If you take the tank and you put any kind of obstacle on the bottom of the tank, you will see, and you leave, of course, you fill the tank with water, and then you put some colored dye. You will see that after some while, when the rotation has been established, the dye will behave like curtains, okay, like column, because of course that is an example of geostrophic flow. Even if smaller, of course, you have to calculate very well the correct rotation frequency. But in that case, you have homogeneous flow. You can fix your geostrophic hypothesis, and when you put some colored dye, you will have the formation of Taylor column. If you look on Google Taylor column, you will find many of these video with this experiment. Okay, actually, I also did it in the past. I also showed some of this, but now the video are not very good. Okay. Very good. So, we have completed the part related to the geostrophic and barotropic flow. We have understood the importance of the conservation of specific quantities, like the volume, the vorticity flux, and the potential vorticity. And now we want to make a step ahead, of course, and start to consider a fluid which actually, a flow which actually fills the bottom. So we want to recover the yeah.
I have a little confusion with the shallow water approximation, that it's assumed that it's far from boundaries.
Yeah.
But the
Yeah.
what we've been doing now is like
Yeah,
we change
because what we said at the beginning is that we are going to allow slip. So we are far from boundary. But in the same case, that's why I was telling that we have to take some, let's say, specific caution to consider the GFD phenomena. At the same case, so we are saying that here we are allowed to move, so the shallow water model said that you can move your column, but there is no difference in the vertical. So the velocity that you have close to the bottom, it's exactly the velocity that you have at the middle of the depth or at the surface, okay? This is something which is not real, I understand, because what you expect is that when you are close to the bottom, the velocity is zero. And what you have, when you are in the internal part of the fluid, will be different from zero in order that you have something like this, which is more real, more, the intuition says like that. But the problem is that the shallow water equation don't have second derivative. Because we said that Ekman is much smaller than 1. And when Ekman is much smaller than 1, the inertial friction, which is the term which basically is related to the second derivative of velocity, is neglected. So neglecting this, in your differential equation, you lose one boundary condition. And one, because you just need one boundary condition, which is, for example, the fact that you have the value of the height, for example, or the initial condition if you want to take the time derivative. So one of the boundary conditions that we lost is exactly this one. So we can say that U and V can be different from 0 when Z is equal to 0, okay? So this is the sleeping condition that we allow when we are working with the geostrophic and barotropic flow. What we said at the beginning, it was something like a sort of act of fate, when we said, okay, let's think that the barotropic and the geostrophic flow, and therefore also the shallow water model, don't fill the bottom. So the fact that they don't fill, it means that the bottom or the solid boundary doesn't have any effect on the flow. Okay, so there is nothing that put in account that relates the flow with the fact that we have a bottom. But we can work with the bottom, as we said before, and we can make all this nice consideration about the conservation of volume. So it's a little bit subtle, if you want, but it's something that helps us to make to consider one aspect at a time. That's why now we want to consider it. So now we will start to include in our equation the friction. So for that, we will remind the so-called Prandtl Hypothesis. So Prandtl was one of the other big names in fluid dynamics, and he said, okay, if we have a flow which is flowing in some direction far from the boundary, and then we have a boundary, we can consider two different sections of our vertical section. So the one which is farther from the bottom, we will call it interior. Okay, the interior will never fill the bottom. The one which is close to the bottom we'll call boundary layer. Okay? So now it means that we will have a geostrophic interior or a barotropic interior, as you like, so it depends. And we just start to understand what happened in the boundary layer, because now we know that at the boundary layer, if this is Z, so when Z is equal to 0, U and V will be 0. When Z will be, let's say, much larger than 0 or tends to the infinite, because we can consider a semi-infinite plane, U will be equal to U bar, V will be equal to V bar. Well, U bar and V bar are just perfect. Okay? So our equations, well, before the equation, so how much can be Ekman? So Ekman, that is the ratio between the vertical friction over the Coriolis acceleration, is equal to me omega h squared. So h, actually, capital H, is the scale of the interior. Okay? While the boundary layer, we will have a scale which is D. So we can say that H is much larger than D. This is an hypothesis, okay? So we can say, okay, we have an interior which is so deep, and the boundary layer which is very, very thin. So let's try to consider this. Okay, now we can consider kinematic viscosity molecular, 10 to the minus 6. Of course, they will be very, very small, because omega, if we are at the mid-latitude, so you remember omega is ordered minus 5, okay, 7 to the minus 5. So if we consider at the mid-latitude, we have a term which is, let's say, about 10, sorry, and what we will have is about 10 to the minus 4 second to the minus 1. So this is square meter over second, and h, for example, let me take for the ocean, can be 1,000 meter. Okay? So if we consider also eddy viscosity, so it's 10 to the minus 2, what we obtain? So we will have 10 to the minus 2, 10 to the minus 4, and then we have 10 3 to the second. Okay? So this is 10 to the minus 6. Then we have 10 to the minus 10 to the 2. And so what we obtain is 10 to the minus 4, which is quite smaller than 1. Okay? Okay, so what happens if we are in the boundary layer? So in the boundary layer, I'm saying that Ekman is order of 1. So in the boundary layer, I am imposing that Coriolis force and the vertical friction are of the same order. So they are equally important. So far from here, no second derivative, no friction. My flow is just trophic or barotropic, doesn't feel the bottom. As soon as I'm approaching to the bottom, I'm starting to feel the friction. So I'm starting to have a second order derivative, which is no longer 0. So it means that these two terms become equal. So we can again rewrite nu omega no longer h, because the scale of the boundary layer is d. So we can solve this with d, because we have everything. So d is actually the square root of omega divided by the viscosity. Okay? Sorry. It's the opposite. Okay? So never forget, when very, very important lesson of life, when you are working with this sort of formulas, always ask yourself if the dimensions are correct. Okay? So before I was I was puzzled because I made an error and I put this on this. But if I continue and I calculate the length, the unit of measure of this one, I am expecting that this is a length, of course, and I will not obtain a length if I have this one reversed. Okay? So always check, because this will be things that it will be asked at the exam. Okay? So making this sort of analysis, scale analysis, let's say short calculation, will be part of the exercise of the exam. Okay. So again, 10 to the minus 2, 10 to the minus 4. So what we have is 10 to the 2, so we have 10 meters. Okay? So 10 meters with respect to 10,000 meters. Can you understand? So we have that this boundary layer is 1% of the interior scale. So it's very, very, very thin. But even if it is thin, it will have very important consequences on our flow. So another interesting thing is that this kind of value of the boundary layer, we can call it also boundary layer thickness, or also some people call it Ekman layer. So maybe you are asking, who was this Ekman? So Mr. Professor Ekman was a Swedish oceanographer, which actually was a student of another very, very big scientist from Norway. His name was Nansen. Nansen was a professor and was actually professor of Ekman. So Ekman was his student. And Nansen, you can find more or less all of this in the Wikipedia, of course, but also on the book. But it's a very nice story because Nansen built a ship which is called Fram. if you go to Oslo, if some of you will go to Oslo to make, for example, PhD, you can go to the museum and there is the ship from, very beautiful, conserved, with all the story of Nansen. So Nansen was a professor, was an experimental oceanographer, and organized a series of expeditions to the Arctic Ocean. And what he did was to go with the ship, wait that the ice pack was formed, and wait that the pack actually completely blocked the ship. So within the ship they had everything: food, they had a piano, they had, of course, scientific tools, they have a lot of instrumentation because they were scientists. Okay, so, and what he observed was that looking at the icebergs were never floating over the same direction of the wind. So this was something that puzzled his mind. How is possible? So the wind is going this direction and the iceberg is going in the other direction. Why? So I know that the iceberg is 80, maybe 90% below the surface of water, but why, if the wind is going like this and I have something in the air which is flowing parallel with the wind, it is not happening with the iceberg in the ocean. So he asked to Ekman to write his PhD thesis on this problem. And Ekman actually created the thesis with the theory which actually brings his name, and is the theory of the Ekman layer. In particular, his thesis was on the surface Ekman layer, while the first example that we are looking now is the bottom Ekman layer, which is practically the same. Okay? The only difference is that related that here we have a solid bottom where the velocity is equal to 0, while in the surface Ekman layer the bottom, let's say, is not solid but is the interface between the water and the air, and what we have there is the wind, the stress of the wind. Okay? So actually there is a strong discontinuity in density because you pass from 1000 to 1 kilogram per cubic meter. Okay, so I think I will just introduce you the equations for the bottom Ekman layer, and tomorrow we will complete. So the equation of Ekman layer, so we are still considering these two, the Rossby numbers much smaller than 1. The Ekman number, as I told you, is much smaller than 1 in the interior, but order than 1 in the boundary layer, and we are still considering homogeneous fluid. Okay? So from this, we are very happy because, of course, we do not have the variation in time of the velocity, we do not have the advection term. So the only thing that we have are the two Coriolis parameters, the two Coriolis terms. Then we have the two pressure terms, and then finally we have the frictional terms. Again here I'm using nu, but you can actually use the eddy viscosity. Ekman in his model, and possibly this is one of the major limits of this model, used a constant value of the viscosity, because if you consider a viscosity which is function of z, well, it is not so easy to demonstrate. I mean, it can be done. There are, of course, if you look on, I also write a paper on Stokes Ekman layer, where we suppose it to take into account an oscillating flow, so like a tidal flow, so moving with the pressure gradient which is changing in time, which is rotating. Okay, so Stokes layer is the oscillating boundary layer plus the Ekman layer. So, and we made some hypotheses and so on. So these are the equations. And of course, also we have the third equation, and obviously we have the continuity equation. Okay? So the boundary conditions are this one. Okay? So tomorrow we will see how Ekman actually solved this problem. Yes.
You need 10 euro?
Yeah, for
I pay
charging.
you 10 euro, not 10 euro.
Not only bless you, but bless you go away.
Almost.
Because of the health go away. Check out where
I was just like looking at the